So now we know that integration involves antiderivatives. We have a distinction to make. So suppose that uppercase f is a function that is an antiderivative of lowercase f. Then the definite integral has limits a and b, and the definite integral from a to b of f of x dx is the antiderivative uppercase f of b minus f of a. The result is a number. We've talked about that as being the area under a curve or potentially a distance, depending on an application. It can, of course, represent other things as well, but we're going to move quickly to the idea of an indefinite integral. You'll notice it's got the same integral elongated s symbol, and the integral of lowercase f of x dx is uppercase f of x plus c, and that's a function of x. This is what we did when we were finding antiderivatives. And you may recall we found the most general antiderivative and we expressed the answer as a function of x plus c. The analog for differentiation is that f prime at a is a number. It gives the slope of a tangent line at a particular point. And f prime of x is a function. And we spent a lot of time analyzing f prime of x as a function, finding local max and local min and graphing and stuff like that. We are not going to be doing that with indefinite integrals. Here's the thing to note though. When you start a problem where you need to integrate, the first thing you're going to see is the integral symbol, and you're going to see right away whether it's a definite integral, which means the answer is a number, or an indefinite integral with no limits, in which case the answer is a function, and we're going to include a plus c, which is called a constant of integration. And the vast majority of the time, we're not going to bother even finding what the c is. We're just going to find an antiderivative. Let's see what this work looks like. We're asked to find a general, or the general indefinite integral. And we're looking at the integral of u squared plus 1 over u squared du. The first thing I'm going to do is rewrite this so that 1 over u squared is in exponential form. So I have the integral of u squared plus 1 plus u to the negative 2 du. That'll be make it just a little bit easier for me to use the power rule for integration. Notice because my integrand has multiple terms, I have parentheses. And each term here is going to use the power rule because we're looking at a polynomial. So u squared becomes 1/3 u cubed. 1 integrates to u. And then if I add 1 to the exponent of u to the negative 2, and then divide by the new exponent, that becomes negative 1 over u. See, that new exponent is negative 1, so it's 1 over u. And when I divide by negative 1, the plus becomes a minus. Plus a constant of integration, and that's it. Our next example involves trigonometry. We are looking at the integral, indefinite integral, of the secant of t times the quantity of secant of t plus tangent of t dt. We do not have a product rule for integrating in the same way we have a product rule for differentiating. And so I'm going to distribute in the integrand. And we have here, when I distribute the secant of t, I have secant squared of t plus the secant of t times the tangent of t. Now, that's multiple terms, so I'm going to use parentheses here, dt. Now, we're looking for an antiderivative. And so we're going to recall that the derivative with respect to x of the secant of x is equal to the secant of x times the tangent of x. And the derivative with respect to x of the tangent of x is equal to the secant squared of x. Therefore, when I need to find the antiderivative of the secant squared of t, that's going to be the tangent of t, right? I'm using the differentiation rule for the tangent in reverse. Likewise, when I need to anti-differentiate the secant of t times the tangent of t, I'm going to use in reverse the differentiation rule for the secant. So my answer is the tangent of t plus the secant of t. Don't forget the constant of integration.